We present a framework that enables legged robots to learn agile skills by imitating animals. Animals can perform impressive feats of agility. Legged robots have also demonstrated the physical capabilities needed for agile skills. But designing controllers for these skills is a time-consuming and difficult process. Imitating animal behaviors can be a general approach to learn controllers for a rich variety of skills. We present a framework for learning robotic locomotion skills from animal data. Our framework consists of 3 components. First, given motion data recorded from an animal, we retarget the motion from the animal's morphology to the robot's morphology. Next, we apply reinforcement learning to train a control policy to imitate the motion in simulation. Finally, the policy is transferred from simulation to a real robot via a sample-efficient domain adaptation technique. Real-world animals will often have a different morphology than a robot. Therefore, before the robot can imitate the animal's motion, the motion is first retargeted to the robot. To retarget a motion, we first specify key points on the animal's body, such as the feet and the hips. Corresponding key points are then specified on the robot's body. Key points are then extracted from each frame of the motion and mapped to corresponding key points on the robot. Inverse kinematics is then used to compute a kinematic pose trajectory for the robot that tracks the key points. This technique is used to retarget motions recorded from a real dog. Once the motion has been retargeted, reinforcement learning is used to train a policy to imitate the motion in simulation. The policies are trained using a reward function that encourages the policy to minimize the pose error between the reference motion and the simulated robot. The same reward function is used to learn all skills. After training in simulation, domain adaptation is applied to transfer the learned policy to a real robot. To facilitate transfer to the real world, we randomize the dynamics of the simulation during training. The dynamics parameters include mass, inertia, motor strength, motor friction, latency, and lateral friction. These parameters are then also collected into a vector and encoded into a latent dynamics representation. The latent encoding is then passed as an input to the policy. When transferring the policy to the real world, the encoder is removed, and we directly search for a latent encoding that enables the policy to execute the skill with the real robot. Before adaptation, the policy is prone to falling. After adaptation, the policy is able to better maintain balance. Adaptation is performed using approximately 50 trials on the real robot. Our policies are able to imitate different gaits from animal data. Our system can also imitate motions from artist-generated keyframe animations. Our policies can also learn this dynamic hopping motion with a significant flight phase. Our system still has difficulties imitating some challenging motions, such as this running man dance move. Next, we compare our method to baseline policies trained without domain randomization in simulation, and policies trained with randomization, but does not perform adaptation in the real world. The other methods struggle to cope with differences between simulated and real-world dynamics. Our method is able to better transfer policies to a real robot. We also compare our learned policies to the built-in controller from the manufacturer. Our approach is able to learn faster gaits. More details are available in the paper. Thanks for watching.